Hello, everybody. Welcome on behalf of the Center for Crisis Studies and Mitigation at the University of Manchester. My name is David Schultz, and I'm a professor of synoptic meteorology and PI of the center. The purpose of our center is to develop a wide network to bring together different researchers across the university working on natural hazards and their impacts on society. Anyone can join, so please get in touch if you're interested in being a member. You can sign up for our network on our webpage. To stay informed of our activities, you can also follow us on Twitter at Crisis Studies. This is another one of our continuing webinars in this series that we've been running for the past 18 months. Seems like, well, sometimes it seems short, sometimes it seems long, but we've been doing it for quite a while. Many of our seminars have been recorded and are online at our YouTube channel. The format of today's talk will be as follows. During the seminar, you can enter your questions in the chat box. You can enter them for everyone to see, or email them or mail them directly to me. We'll do our best to get to them all during the question and answer session at the end of the talk. For now, let me introduce our speaker. This is Dr. Ben Parks. He's the Ekpe Research Impact Fellow at the University of Manchester in the School of Engineering. His work focuses on how large-scale climate change affects human livelihoods. Now, the title of his talk is quite provocative: Evaporative Coolers and Climate Change in Africa, the Tyranny of Thermodynamics. And I'll pass it over to Ben here shortly, but as an atmospheric scientist who lives by the thermodynamic equation, quite surprised that it can be tyrannical at times, but I'll let Ben explain what he means by that. Take it away, Ben.
Thank you, David. I'm just going to share my slides. Okay, yes, so I have put myself with a bit of a target with saying, yeah, the tyranny of thermodynamics, but I do hopefully have a good explanation for why I've said this. So we'll just jump straight into, well, we know what Africa is, got to know well, where Africa is, we know what climate change is. Let's talk about heat stress. What is heat stress? It is the inability of a person, creature, or a system to maintain thermal stability under any given set of conditions. Now, this could be an overclocked computer part, it could be a green shoot succumbing to frost at the start of a year, or a person fainting from heat. Now, humans are the topic of interest for me today, so I'll be focusing on them. Hypothermia, unusual word, which is one that does exist, is the excess of heat. And this is associated with high temperatures, but I do hope to get people looking a bit beyond temperature today, not just focusing on the thermometer. At the other end of the scale, we have hypothermia, which we have heard about. It's cold stress. Now, the images I'm displaying here are a quick online search, just using an image search of heat stress and cold stress. And we can see the standard things that you find when you look at these topics. I am focusing on Africa and on climate change. Cold stress isn't going to be a high priority. So from now on in this talk, when I say heat stress, I am meaning high temperature heat stress. So if I was in person and this talk was going on in front of a seminar audience, I'd actually be a bit mean now, and I'd ask for people to shout out their thoughts of what are human responses to heat stress. But given we're doing this over Zoom, it doesn't really work too well. I'm just going to put up a list of common responses to heat stress. And if you're feeling brave, and please do, suggest a couple more in the chat. Now, one human response is to drink water. Another is to seek some shade, stop doing anything busy, or even go to a cool environment. And they're all viable options. However, if you're working in a field, maybe you don't have any shade nearby, and if you are working, then stopping work isn't an option. Cool environment may also not be available to you if you're doing outside work, planting, harvesting, any work in a farm, for example. Typically, a response is fans blowing air around, but that's what they do. They move air around. If the air temperature is above about 36 degrees Celsius, then a fan will probably end up doing more harm than good. You'll be blowing warmer air onto the surface of your skin. So beyond fans, you're looking at powered cooling of some sort. And I'm using the phrase powered cooling deliberately, slightly vaguely, because it is a complicated description we've got coming up. This is an example on the photo. I did a bit of research to find what is an example of people responding to heat stress. And this is Glastonbury, one of the years when it didn't turn into a mud fest. You've got a lot of people huddling under a tree to avoid the sun because they were just seeking shade. So moving on from this, there are three different cooling methods that you can use for a building or a room. And I've got them ranked here from highest to lowest cost. A heat pump can move heat bidirectionally, so it can be used to either heat or cool a room. Air conditioning, the next one down, generally only moves heat in one direction. And these are both intensely powered mechanisms. They are common in the developed world, and they're often used by affluent people in the developing world. Evaporative coolers have been nicknamed swamp coolers. And if you've ever been around them, you'll know exactly why they're nicknamed swamp coolers. They do smell awful. That's because they're designed, and there are a few different designs. The mechanism is still the same for them. They evaporate water, and they use the energy requirements of evaporation to draw heat from the environment. And it can be as simple as a fan blowing across some straw soaked in water, like the example I've got on this slide. And this is where they get the nickname swamp, because that wet straw will start to rot, and that's where the name comes from. You can also have ones that project a fine mist out of calibrated holes in a hose. In most cases, evaporative coolers are cheaper to buy and operate than the other counterparts, and they are common in the developing world. Now, for our study, we simulate two different evaporative coolers, one that is 65% efficient and one is 85% efficient. The thing with evaporative coolers is they have a hard limit to how far they can cool the environment, and that's the wet bulb temperature. Because they evaporate moisture into the air, there is a point at which the air will take no more moisture, and that's as cool as they can bring it down to. The low efficiency coolers reflect their ability to get to the wet bulb temperature. The low efficiency coolers are common at domestic scales. The 80% efficiency ones, the higher efficiency ones, are more common at large industrial scales. And the next thing I want to bring us onto is estimating heat stress. And there are dozens of different heat stress metrics in the world. There's apparent temperature, which we'll be using, there's humidex, there's the wet bulb globe temperature, there's the discomfort index, and there's a few other commercial variants like real feel or feels like. I am genuinely half tempted to propose the idea of a cold stress variant called big coat. And all it will be is a single piece of information which tells you, do you need your big coat today? It might be fun. Moving on to actually estimating real heat stress. This is the apparent temperature equation. And because I'm using a lot of climate model data, I've got access to a decent number of variables. So, and apparent temperature has been parameterized in a few different ways. This is the version we're using. It is a function of temperature in Celsius. Small e RH is the vapor pressure in pascals, which we've derived from relative humidity. And U subscript 10 is the wind speed at 10 meters. So the apparent temperature takes into account water vapor. And this is important. This is why I want to get people thinking beyond the thermometer today. Humans lose heat by sweating, and then the sweat evaporates, and that draws heat energy away from the body. The wind speed also carries air away from the surface. In this case, it would be the surface of the skin. I've got two values that I've used for this metric. I've got an AT value of above 28 to define slight heat stress and above 32 for moderate heat stress. These are published values from other papers, but I do want to acknowledge there's a criticism of pretty much every heat stress metric that exists. They are built for the person they are calibrated for. And that means that they may not necessarily apply everywhere and to everyone. Taking this into account, I've done all my analysis for both slight and moderate heat stress. The slight results may not necessarily be apparently useful for Africa, depending on the calibrated groups that we use to derive the apparent temperature. Healthy people conditioned to a higher level of apparent temperature may be fine at the value of slight heat stress here from this calculation. But if you've got someone who is vulnerable, someone who is has an existing health condition, someone who is not getting enough food, that may not be the case. So I'm still going to present the apparent temperature values for a value of 28. Now, I have mentioned a few times, I've talked about climate models. For anyone who's really fussed for the names of the climate models, these are the 18 that we've used, and they are from CMIP 5. Now, you'll see on there, if you're very quick, there are 2 from CCSM 4. This is because we had different couplings for the input data. One was either coupled directly to the surface or just the lowest model level. You'll also recognize there are some models that are part of CMIP 5 that are not in this list. We required 6 hourly data for our analysis. So HADGEM is omitted from the list as well as a couple of others. This work was a collaboration with Jonathan Booz and Matt Huber. Jonathan is based in Bern and Matt is in Purdue. And we've built a hypercube of the relationships between the thermodynamic variables in the model, effectively an emulator. So despite the fact that some of these climate models respond to greenhouse gas emissions with different sensitivities, you may have heard the phrase climate sensitivity, and that it is model specific, the underlying physics and the thermodynamics within the models, because they're all based on thermodynamic equations, are consistent. So with our hypercube, we can actually scale climate change between 0 and 5 degrees across all models, even if a given GCM has a low climate sensitivity and didn't reach +5 degrees. Now, admittedly, as we get to higher temperatures, the strength of relationship does begin to weaken slightly. So I'm going to concentrate mainly at what happens at +3 degrees Celsius for results. I will show the +5 degrees ones for completeness more than anything. The really nice thing about this hypercube and the consistent thermodynamic relationships is that we can pull out the relationship between apparent temperature and any other variable. Now, most people's metric, and the one I'm trying to get us away from, is temperature. So we could look at any temperature increase and what that means for the apparent temperature. So that's the climate models. Now, just before I move on to the results, and I'm aware that I'm talking about this fairly quickly, but I'm excited about the work, so you're getting the excited version of me. I want to talk about population data. So the simulations I've got are all based on CMIP 5, and as our scaling can go up to +5 Celsius, we picked a socio-economic pathway that matches this, which is SSP 5, which is a highly fossil fuel development. Now, I agree, especially given that we've got COP26 going on, SSP 5 is unlikely, but it's also not the highest population change. If you look at the population curves for SSP 2 and 3, they do go to higher populations. So when we look at +3 degrees Celsius with population weighting, we're not necessarily pulling out the biggest possible number within that set of circumstances. But when we look at +5 degrees Celsius, they are going to be the biggest possible number because only SSP 5 will result in a climate that's at +5 degrees Celsius. For most of the interesting results, we'll still stick to 3 degrees Celsius. And I'm going to warn in advance, there's a lot of plots that are about to happen to everybody here. And I'm going to try to break these down and not scare people off. These plots show the percentage of the year that people are exposed to heat stress. And if you want to translate this into days, you multiply it by 3.65. The control results are in the top left, and they will always be in the top left of this plot. It's the historic period from 1986 through to 2005 without any space cooling technology, so no swamp coolers at all. Move across the rows, I've got +3 degrees Celsius in the middle and +5 degrees Celsius on the right. So we can see in these plots how as temperature increases, we can see that more of the continent is exposed to heat stress, and that's pretty much universal. Although the Ethiopian highlands do seem to mitigate this somewhat. I did spend a lot of time talking about model setup. This is because the increasing temperatures don't happen in isolation. Temperature changes affect humidity. Pressure differences across the land and sea affect wind speed. The climate is not a simple system where we can move a bar and get a simple result. It's a complex, interconnected system. And our hypercube does a reasonably good job of making this a simple system, but we have actually got all of that complexity built into it. So increasing temperatures can rapidly ramp up the fraction of the year where there's heat stress. Moving on from that point, the second row shows the fraction of the year exposed to heat stress when you're running a low efficiency evaporative cooler. The bottom row is the same with a high efficiency cooler. And in both, we can see the regions with high humidity, so Central and West Africa, are strongly affected with heat stress despite the cooling. And you can see that the dry regions, the Sahara, with its notably low population, has a very effective evaporative cooling system because the air is very dry. Now, I'm going to move on to the next set of results. All of my plot, well, this plot has the same layout, but instead of showing the totals, it is the difference from the control. So we can see where heat stress is becoming more or less of a problem depending on the severity of climate change and the cooling technology used. So without cooling, but with increasing temperatures, we can see that the entirety of Africa is exposed to more heat stress. It's the same result as the previous slide. With, well, the tagline, and something that David did pick up on, was tyranny, and the tyranny of the thermodynamics. And this is the issue facing West and Central Africa. Evaporative coolers, as I said before, saturate the air in an attempt to bring temperatures down to the wet bulb temperature. And the efficiency of the 65% or 80% efficiency coolers is how well they perform this task. The increase in moisture and the limited reduction in temperature means that evaporative coolers cannot provide sufficient cooling to prevent heat stress. And you can see this certainly when you get to +3 degrees and up to +5 degrees in West and Central Africa. Now, the effect would be similar to living in a muggy room, a very hot steam room for 6 or 7 months of the year. Something I find quite interesting in these plots is the lack of difference between the low efficiency and the high efficiency coolers. Either the air in the regions we're looking at can hold more moisture and drop the temperature to something comfortable, or it can't. This is why we keep seeing this band of increase. Another thing we see is the band of increased heat stress along the East African coast. So if you just look down the side of the plots, there and there, you can see that the moisture coming in from the sea is also reducing the effectiveness of the evaporative coolers. Now, I do hope that the leaf blow that's going on outside isn't disturbing anyone, and I'll continue assuming that it's not.
It's not.
Awesome. All right, so I'm now bringing out the population weighted results. And one of the big advantages of our scaling methods is that we have temperature results that are independent of time and thus population change. So you can see what happens if climate change is rapid, and if we have +3 degrees in 2006 to 2035, or if it's slow, and we only get to +1 degree by 2066 to 2099, so the end of the century, although that one isn't shown here. These bar charts show the number of heat stress events based on the SSP5 population changes for the historic and 3 future time slices. So we've got near future, 2006 to 2035, medium, 36 to 65, and far, 66 to 95. The blue bars show the number of slight heat stress events, and the orange bars are on the same scale, and they are the number of moderate events. These scales all top out at around 500 million events, because each person, each day, could be exposed to heat stress. And we can see that population changes drive the total number of heat stress events, which makes sense because each person, each day. And now I'm just going to scale this back to, from a governmental point of view, think of all the extra cooling demand. Many people are going to want to have somewhere cool to be because it is unsafe to be in a temperature that hot. Even with evaporative coolers, when climate change brings higher temperatures, heat stress will be a significant problem. When it actually comes to looking at these plots, I tend to think of them most as a choose your own adventure. Pick a cooling technology, either no technology, low efficiency or high efficiency. Pick the level of climate change. We're looking at what happens at 3 degrees or what happens at 5 degrees. and then pick the time span you're interested in, and you can read off how many heat stress events there are likely to be across the continent. Furthermore, these heat stress events, especially if evaporative coolers are deployed, will be concentrated in the Central and West African nations. This is where the tyranny is really beginning to bite. Developing countries in this region are therefore going to get hit with a double whammy. They've got the problems associated with climate change, requiring more expensive cooling technology to preserve their population. And they have to build the infrastructure to support that cooling technology, or while they are not necessarily the largest contributors to the problem, they can't use the cheap solution, and they're left with the largest bill. That's where the tyranny, these equations are really biting. So I've now got 3 pages of similar plots. So we'll get to the countries as they turn up in the list. The names are generated using a shapefile from Natural Earth, which is a resource for shapefiles, and these are country specific. And they show the cooling technology required to bring the total number of heat stress events down to the historic level. Now, the first thing people have noticed are these polls I've got for Cape Verde, Cabo Verde, and Comoros. And that's because we didn't resolve them properly in our data, and I would much rather show nothing than bad data. The results will be extremely suspect if I try to show anything for something that small. So on these plots, blue means you need no cooling. Orange means that you can use low efficiency coolers, yellow for high efficiency coolers, and then purple for air conditioning. And again, I think of these as a choose your own adventure. I love the phrase. Pick a time, so the historic period, near, medium or far future. Pick a warming and read off what cooling is required. So let's take the example of Angola, and we're going to go 1 degree per 30 years. So with historic, I should also have mentioned, sorry, this is the cooling required to bring the number of heat stress events down to the control simulation. Now, whether or not you think the number of heat stress events in the control simulation is acceptable is a different matter. This is just how many, what do you need to do to make the problems from climate change go away. So back to this Angola example, 1 degree in 30 years, we need the low efficiency coolers. But as soon as we hit 2 degrees in the medium and then 3 degrees in the far future, that's air conditioning. Now, if I were to contrast that with Algeria, which can use the low efficiency coolers in any set of simulations, or Egypt, which uses low efficiency coolers right up until +5 degrees, we can see a difference between the tropical countries and the extratropical countries. Now, I'm going to go back to something I found interesting, is that if a country transitions to air conditioning, they don't tend to spend a lot of time requiring the 80% efficiency coolers. It's either low efficiency or air conditioning the majority of the time, and very little points when you need both of them. So if we move on to the next set of countries, and we can come back to these in the discussion if anyone's got a particular result they want to discuss. Again, the 80% efficiency coolers have got a very short lifespan of usefulness. Liberia and Gabon jump straight to air conditioning. And then you've got other countries that are in the same region that jump very quick as well. Ghana is another one with that case. We also see the first instance of a zero cooling requirement, and that's Morocco. So that is in the bottom right. This is because the population curve in SSP5 is a parabola. So it tends to peak midway through the century and then drop off towards the end of the century. If populations are declining, you have fewer people, which means fewer total heat stress events. I'm going to move on to the final set of these slides. So we see the same general results again. I will mention that Sao Tome and Principe, I'm never certain how to pronounce that. I don't resolve the data there, so I don't present them. But we have this same general pattern I've been going on about. West and Central Africa require air conditioning to prevent excessive heat stress events, especially with high populations or severity of climate change. The extratropical nations are less vulnerable, and under moderate climate change, if you call 3 degrees Celsius moderate, and probably not, they can use the less power intensive methods. Now, something I should mention in all of these results is these are the results required to prevent heat stress. They have no bearing on the number of people cooling for comfort. So this is possibly an underestimate. People with disposable income or people who have got the option to install air conditioning or a heat pump may well do so, and that will be extra strain on the electricity grids. I will also say that the results for cities along the great rivers of Africa, think the Nile is a classic example. Even though they are great rivers, they're not big enough to appear in climate model grid cells. So if you've got the cities of Alexandria and Cairo built along the Nile, where you've got a large amount of moisture from the river, there may also be local heat stress. So our Egypt results from the first of these three slides may well be an underestimate. And I've realised I've gone through this at quite a clip. We're on to the conclusions because I'd much rather have a discussion. And this isn't news. Heat stress gets worse with increasing levels of climate change. In other news, water is wet. In the absence of cooling, it gets worse everywhere. In the extratropics, you can use evaporative coolers to prevent heat stress. And that means that it will at least be no worse than it was in the control simulation. I'm again going to hark back to my slightly emotive phrase of the tyranny of thermodynamics. I know I did use emotive words. I possibly should have said the tyranny of moist thermodynamics, but the word moist causes a strange reaction in people. The thermodynamics issues are that evaporative coolers can only bring temperatures down to the wet bulb temperature while increasing the humidity to near saturation. And that means we have a limit before air conditioning is deployed over Africa. And that really is the end of what I intend to present. And I'm looking forward to a Q&A session with everyone now. Thanks everyone for listening.
Great. Thanks, Ben. Thanks, Ben. Much appreciated. Do we have any questions that people want to either raise their hand or ask the question in the chat box? If not, I'll kick it off. The title of your talk was The Tyranny of Thermodynamics, but your results, I'm wondering how sensitive are they to your choice of heat stress quantity? So, you used apparent temperature. It's just one empirical relationship, certainly sensitive to the relative humidity, which will be changing during this time. So do you want to comment or reflect on what would happen if you choose another thermodynamic equation, thermodynamic variable for your heat stress?
Yes, so I did only in this talk present apparent temperature. I've actually done the analysis using the discomfort index as well. And like apparent temperature, it does have a response to moisture in the system. The results are remarkably consistent. There's a bit of variability about which cooling technology is required when, but because pretty much all of the heat stress metrics are some measure of temperature and humidity, the response of setting the wet bulb temperature or setting the humidity to 100%, even if you bring the temperature down, means you get a very similar response.
Great, thanks. Paul, you had a question.
Yeah, hi. Great talk, Ben. A quick question. Can you talk a little bit also about, let's just say, land use changes over the next 20 or 30 years in Africa? In other words, if rangeland or farmed areas is being changed into something else, obviously that's going to change evaporation. Things that may have had evapotranspiration, such as crops, may be replaced by things that aren't crops. So, did your studies include anything about changing land use and how that may be affecting some of your conclusions or influencing your conclusions?
All right. Okay. So, question about land use. We don't have any information about land use in the input data, so we would end up having to use other people's results to comment on what it means for land use change. The population data that we have contains a small amount of information in a related sense, because you have the case of increasing urbanization and an increasing urban population. Unfortunately, because we had to use climate model data to get 100 years of data for 18 models, the grid boxes are so coarse that we don't really factor that in too well. I think my concern for the infrastructure requirements to power this cooling is more focused on the urban areas where there's going to be this high density of people. In the rural regions, population is likely to decline in most simulations. I probably haven't really answered your question, but I don't have anything better to give as a response.
Any follow-up to that, Paul?
No, I mean, certainly urbanization is going to be a factor. As you mentioned, people that are going to be maybe congregating more into the urban areas are going to be more densely packed, and there could be less evapotranspiration there. I guess I was focusing my question more on I guess the rural areas and how they were, if they're being exploited for their resources and it's changing the land use, how that would affect just the overall implications of your model. That's all.
Well, if we just take the simple approach for heat stress, if there is less moisture in a similar temperature, that does reduce heat stress. So if they're no longer exposed to an awful lot of crops, it may reduce their personal exposure. But it depends on what you're replacing with. If you're replacing a farm with a mine, where people are doing a lot of very intense physical labor in a condensed group, it's probably going to be worse. But I think we'd have to do a proper study on specific land use cases to get a definitive answer.
Thanks.
Any other questions or comments? If not, I'll ask another one. You mentioned obviously that the climate models don't resolve rivers and small scale, mesoscale weather phenomena that may be influenced by that. And you say that this may lead to an underestimate of it. I wonder also if there wouldn't be places that would lead to an overestimate, such as if you don't have, if you're not capturing the sea breezes along coastal cities very well in the climate model, then people may experience cooler environments during otherwise hot periods that would be detected in the climate model. Actually, if you had a higher resolution climate model embedded downscaled or mesoscale model, you may actually get more relief. But again, obviously this is just speculation.
Yes, and it is an interesting point to raise whether or not the sea breeze will bring relief. It depends really where you're sitting on the heat stress values compared to the temperature and moisture values. If the sea breeze lowers the temperature by 5 or 10 degrees, then you're probably okay. But if it's only 1 or 2 degrees and brings in more moisture, it might make it worse. And for that, we do need to do some proper high resolution runs to have a look at the results. I have seen some papers, I can't remember the author, where they've done something similar to this using the large rivers in Africa, and you can actually see a spike in heat stress just from the river areas. It's not the same as a sea breeze, but a similar set of circumstances.
Yeah, and I guess also it depends on whether those river valleys are vegetated with lots of canopies and so forth. Again, well beyond the capabilities of a large scale general circulation model, but still,
Yeah,
it won't change the essence of your results. It's still not heading to a good place no matter what. But again, just
there is
things
definitely
here or there.
room for improvement in the results using more high resolution data.
Yeah. So there's a question in the chat box from Chris. Did the country specific results for future cooling methods match expectations, or were there particular surprises in your results?
I don't think that they were necessarily surprising. If you had told me that evaporative coolers are better in dry regions than moist regions, I'd probably have gone that tracks. That makes a lot of sense. So I try not to approach results with an expectation. I think that these results follow what you would naively expect to see, where tropical regions with a high moisture loading throughout the year are more vulnerable to heat stress. I think I think actually the thing that surprised me most is just how good the coolers were and how little you needed the high efficiency coolers. When you could get away with a very cheap system in the driest regions. Now, admittedly, a lot of those dry regions are bordering the Sahara Desert or on the Mediterranean Sea, and we have to again account for the amount of moisture coming in off the Mediterranean and the low population in most of the desert regions. So in a lot of these countries, the population is concentrated along the coast. And to get realistic results, you probably have to do some more high resolution simulations.
What's the difference in cost between the two types of cooling systems?
I can't tell you that one off the top of my head.
Oh, okay. I was just wondering if it was like factor of 2 or a factor of 10, or
I
you know,
think
obviously air conditioning is going to be a lot more expensive than you know, swamp coolers, but I was just wondering between the two efficiencies.
I think it's more a factor of design and scale, because the large scale ones, the high efficient coolers, are run at an industrial scale. You can take advantage of a few of the economies of scale to get something that runs at a higher efficiency.
Hmm. And I guess also to follow up on Chris's question, is it the quantification of these ideas? So maybe the basic results, as you said, water is still wet in your conclusion. The basic results were kind of predictable, but is it the quantification of how poor the situation is going to be for people in Africa, regardless of the trajectory of climate change?
Yeah, that's one that when the results came out, it was a sort of sit back and go, oh, that's bad. That it was an unpleasant realization that with plans in advance, even if we started doing things now, you'd have to ramp straight to air conditioning in some cases. And even if you didn't, you've got to be looking at supplying air conditioning for the majority of the population by 2036. That's a lot of energy that you need to be able to reliably provide. And with the best of will, the electricity grid in Africa is not that robust.
Any other questions or comments? Okay, well, then let's thank Ben once again. And I've put some links to our website if you want to sign up for the network. I've also put in our Twitter link and then the link to our playlist on YouTube that contains many of our past seminars. We don't have the next seminar in place yet, but if you watch those resources, we'll make sure to get that announcement to you. Thanks a lot, everybody. Thanks again, Ben, and everyone have a good rest of the day. Bye.